In this chapter, we will be studying limits. In this lesson, we will be focusing on one-sided limits.
Okay, everybody. So in this next lesson on limits, we're going to talk about one-sided limits. Okay. So now we've already seen when you're defining a limit that you need to be able to approach a value from both sides. Okay. And we've even talked about what happens if you approach from one side as opposed to the other. Well, now we're going to focus a little bit more specifically on exactly that sort of a thing here, one-sided limits. And to do that, we're going to go back to something you would have seen maybe a course or two ago, this thing called a piecewise function, okay, where the function has a different definition, okay, based on what part of the domain you're working or you're looking at. So here, for example, this particular function f of x is going to equal 1 so long as the value of x, as long as we're in the domain where x is greater than 0. No, not even or equal to, just greater than 0. So moves on like this. This is a value of 1. Then it also has a value of 0 as long as x is less than or equal to 0. So in the domain where x is less than or equal to 0, it rides along the x-axis. Now this has a really abrupt jump at x is equal to 0. Okay, as we go along, we get to here, it's defined here, then all of a sudden, boom, it's defined up here and keeps going. And we would call this a step function. Okay, that would be the name that we would give that there. Now, let's take a quick look here. If we approach, so what we're going to do here is we're going to find the limit. The question here, and it's not actually even written there, it's going to be to find the limit as x approaches 0. Now, if you approach 0 from the left, okay, if you approach 0 from the left, now, the part of the function that we're dealing with here, approaching 0 from the left, is going to be this part right here. This is the part of the domain that includes the values that are to the left of 0. Now, my experience with this, where students get frustrated or get confused by this, is because they fail to recognize that this is the part right here that we're dealing with. This is the part of the domain we're dealing with where x is less than 0. And the value of the function right there is 0. So that's why, as we approach x from the left of that function, this right here is the part of the function, the definition that we're going to use, that guy right there. And it turns out that the answer is therefore 0. And that makes sense. As you ride along the graph, approaching this value right here, as we ride along, it looks like we're going to get a y-coordinate of 0. However, if you approach it from the right, okay, if we approach it from the right, this time we're using this part of the function right here. And that's because in the domain here, this is where the function is defined on the right-hand side of 0. Okay, to the right of 0. So now, if we ride along this function here, it looks like we're going to get a y-coordinate of 1. And that's because we are always riding along this part of the function. Okay, this is the part that we're using. So the answer is 1. So approaching it from the left, approaching it from the right, is giving us two different values here. Okay, so the two-sided limit, okay, approaching from the left and right, does not exist. We need the left limit and the right limit to be the same thing in order for the limit to exist. Okay, so in general, what we say, okay, is that if the limit as x approaches some number from the left doesn't equal the limit as x approaches that same number but from the right, then the limit doesn't exist here. And that's what we're seeing up here in this particular function. As we approach it from the left, as we approach it from the right, we're not getting the same value. There is a jump in this graph, and that's because there's a discontinuity here. Okay. Now, if, however, the limit as x approaches a from the left the limit as x approaches a from the left of f of x is equal to some number L, and that also happens to be the number that we get, the result that we get as we approach a from the right, then we can say that the limit, now there's a couple things that we say here. This kind of summarizes here. There's two bits to this. First of all, we would say that the limit as x approaches a of f of x exists. Okay, we know that it's going to exist because it's the same from the left and right, and it's going to equal that value L. Right? Now let's go through and let's take a look at an example of how this plays out. And we're going to look at, again, another piecewise function, but a slightly larger one. Okay, everybody, so here's our question. If f of x is equal to, we got this piecewise function, negative x when x is less than negative 1, x cubed when x is between negative 1 and 1, and x when x is greater than 1, then we're going to find, we got this set of limits here that we're going to work through. Now, I am going to graph this in a bit here, but before I do that, I want to go through and take a look at these limits, okay, without, okay, I want to take a look at these limits without going back to the graph here. So for example, this is, we're going to take a look at the limit as x approaches negative 1 from the left of f of x. Now, we shouldn't need, okay, we shouldn't need to have to go to the graph to figure this out here. And that's because when we take a look at that limit there, I'm approaching negative 1 from the left, okay? That means this interval right here, okay? This is the function that applies when the value of x is less than negative 1 or to the left of negative 1. So now what we'll do here is we're going to use that negative x there. So this is going to be equal to the negative of negative 1. And so my answer is, what is the limit as x approaches negative 1 from the left? Well, it's going to be positive 1. Okay, take a look at b. This is the limit as x approaches negative 1 from the right of f of x. Now, in this case right here, what we're dealing with is the interval here that includes values just to the right of negative 1 or greater than negative 1. Well, right here I see x greater than negative 1, meaning this is the function that I'm about to use. So then in my limit here, I'm going to take and plug in that negative 1, but this time the function that I'm applying that to is going to be the cube, and negative 1 cubed is going to, whoops, wow, can't believe I wrote that. Okay, negative 1 cubed is going to be negative 1, which means, part C here, that the overall limit as x approaches negative 1 of f of x does not exist. Okay? Does not exist because the left-hand side and the right-hand side don't equal each other. So there's a discontinuity going on there, okay? Now, let's take a look at what happens with this other limit here. Now I'm gonna start this this little note again. Okay, actually what I'll do is I'll erase all of this. And we'll do this again with this other set. So we're going to now look at the limit as x approaches positive 1 from the left. And this is D. The limit as x approaches positive 1 from the left of f of x. Notice what that is. Okay, positive 1 from the left. X is less than positive 1. So again, we're working with this function right here. So that is going to be 1 cubed. And when we do that, we're going to get positive 1. Whoops, sorry, I don't want to do that quite yet. I want to do E. This is going to be the limit as x approaches positive 1 from the right of f of x. This is going to be right here where x is greater than 1. So it's this function right here because this is the interval over which that's defined. And so now I know that that's just going to be that function x. So I'm just going to plug 1 in. And because it's just x, that is the answer here. So for f, when it asks what is the limit as x approaches positive 1 of f of x, because it's 1 here and it's 1 here, those are both the same, the answer is that the limit as x approaches 1 of f of x is just 1. Okay? Now, let's take a quick look at what the graph of this thing is going to look like. We'll delete all this. Erase all this, I should say. It's probably a quicker, easier way to do that, but I'm just learning how to use this machine right now. So here's my grid. My points that are of interest to me are down here at negative 1, out here at positive 1. So I know that my first function right here, whoops, oh, I lost my note. Okay, I know that my first function, we'll pull that back up again. Oops. Okay, we'll do that again. Here's -1, here's 1. The very first function is negative x, but it only applies where x is less than -1. So it's only going to apply in the interval here, and maybe what I'll do is I'll switch colors here. We'll use red. It's only going to apply over here to the left of this one, okay? My second function, the x cubed, let's maybe use green for that one, is only going to apply in this section right here in between those two, okay? And that last one where x is greater than 1 is only going to apply right here. So let's go back to my red, okay? Negative x is going to have a slope of -1. It's going to have a y-intercept of 0, but when x is -1, it's going to be +1. So we're going to put a big open 0 right, whoopsie, oh boy. I'll erase that, we'll do that again. It's going to have a big open circle right here because it's not defined there, and it comes down towards it at a slope of -1. In between these two, the function that we're using is x cubed. Now, x cubed has got that kind of an interesting little stereotypical little S curve right near the origin. When x is -1, it's going to be down at -1. When x is +1, x cubed is up here at +1. Because my interval includes both endpoints, I'm going to fill those in. And then the cubic curve looks something like that. Now, finally, my last function here, which is just y equals x, it's going to have, it's only going to apply in this blue section right here. At 1, the y-coordinate is 1. Now, I'm going to put an open circle there because it's not defined in that interval, but at the same time, that point was already filled in. And then this is going to move away with a slope of 1. So you can see right now, even from this graph right here, okay, we've got an abrupt jump right here, this discontinuity. It's because the limit as we approach -1 from the left, and then as we approach it from the right, they are not the same thing. We are not pointing at the same y-coordinate. However, over here at 1, as I approach it from the left, approach it from the right, we are approaching the same value, so the limit does exist right there.
Now we'll take a moment just to summarize what we've looked at thus far.
Everybody, so this is that graph that we were just looking at here. It's just, in this case, it's graphed a little bit nicer. I used a program to do that. Notice that the graph is discontinuous when x is equal to -1. Okay, that's that gap right there. It is continuous, though, at 1, okay? Because not only is it defined there, the limit exists as we approach it from the left and right. Now, this means, however, that the overall function has to be characterized as discontinuous, okay? If there's a discontinuity anywhere, the function is discontinuous, okay? So just bear that in mind as we go through, as you go through your questions here. Now, just really quickly before we finish this, in general, if we're going to talk about continuity at a specific point here, that occurs when the limit as x approaches a of f of x is equal to f of a. Now, we've already talked about that, but just to reiterate this again, what this means is, what is implied here is that, first of all, the function is defined. F of a is defined, so a is in the domain of f. Because as soon as you're talking about where it's not defined, like there's either an asymptote there or there's a hole there or there's a gap there, it's got to be defined to be continuous. The limit has to exist, okay? So bear in mind, it is possible for a limit to exist and the function to not be there. And I'll draw a picture of that in just a second here. And then lastly, that limit has to be the same as that particular function, okay? When just one of those things fails, the function is not continuous at a, so that we know that's discontinuous. Now, let me go through and show you something here. So let's go through. I'm going to draw a quick picture here so that you can see how this works. So because it is possible that the limit exists, but the function doesn't. So let's say you had a graph here. Okay, so notice the limit, and let's throw just a number here. Let's call this C. Let's call this D. The limit as x approaches C of our function here, f of x, well, as I approach it from the the left, I'm getting d. As I approach it from the right, I'm getting d. So the limit as x approaches c of f of x is going to be d. However, notice that there is no value there. Remember that the limit doesn't require that that value that we're approaching be in the domain of the function. Okay, with all the talk about the limits and the delta notation, all that stuff, blah, 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 that we said, it was always the case that if you were approaching, that as x approached some number c, okay, it didn't have to be the case that c was in the domain. In fact, we might even have the point up here. Okay, it might be, for example, that f of c is equal to e. So the function does exist at c, the limit exists at c, but they're not the same. Okay, they're not the same thing. So again, that is what lets us know that there is a discontinuity. There's a break in the graph, and that's what that was talking about. Now we're going to take a look at just one more example of all this. So now everybody, we're going to take a look at one last function here. And the function I want to take a look at is the absolute value of x minus 10 over x minus 10. And what we're going to do is we're going to take the limit. We're going to find the limit as x approaches 10 of f of x right here. Okay? Because I'm interested in what's going on here. Now, it's important to notice with this particular example, and I'm pulling this one up here because it's a natural piecewise function that you've very likely seen before. I want to first of all notice with this function right here, before we get into the limit, that the domain is such that x cannot equal 10. Okay? Because if x equals 10, then that expression is undefined. And that's going to be important for us as we're determining the limit here as x approaches 10. So now this is going to be equal to the limit, okay, as x approaches 10. Now we're going to have to rewrite this function because it's got an absolute value in it. So in order to understand this, we're going to have to break that apart into its natural pieces here. So we know that x minus 10, okay, x minus 10, in fact, maybe we'll do this over here just so we get a sense of it. The absolute value of x minus 10, well, is going to be x minus 10 as long as that expression is positive, and that's going to be true so long as x is greater than 10. However, we'll put a negative through there. Okay, we'll just multiply negative through. That will be true as long as x is less than 10. And then remember, that negative being multiplied through is going to make that equal to a positive. So that's what we want here. So over here, this is going to be x minus 10 over x minus 10. Because remember, that absolute value is over. Here, let's just change the color here real quick. That absolute value is over this piece right here. And that's why this is right here. Okay, that's why I put that there. That's going to be true so long as x is greater than 10. And then we know it's going to be negative x plus 10 over x minus 10 so long as x is less than 10. Now we can simplify this a little bit. So this is the limit as x approaches 10. Now notice x minus 10 divided by x minus 10 is going to be 1. And that will still be true as long as x is greater than 10. Negative x plus 10, okay, negative x plus 10 is the same as negative x minus 10. So this bit right here, again, I'll change colors. So this bit right here is going to be the same as this bit right here, which means I can cancel out, okay, that x minus 10, and I'm going to be left with that negative right there, okay, negative 1. And that will be true so long as x is less than 10. So now take a look at this. As we approach 10 from the left, okay, as we approach 10 from the left, the result is different from us approaching 10 from the right. So because the limit as x approaches 10 from the left of f of x does not equal the limit as x approaches 10 from the right of f of x, Okay, we know that the limit as x approaches 10 of f of x does not exist. Okay, there is a discontinuity at that point in the graph. And we knew that, though, because it was undefined from the beginning here, but we see that now a lot more clearly.